I'm really pleased to be able to show you a behind-the-scenes tour that most people never get to see of the D. Gary Young Research Institute. So follow me, we'll go in. So here we are in the research laboratory at the D. Gary Young Research Institute. And before I show you around the laboratory, what I wanted to do is point out the floor, believe it or not, because this laboratory is actually built on a separate foundation from the rest of the building. And the reason we did that is because we needed a floating foundation to dampen vibrations, because vibrations can actually upset some of these very sensitive instruments. So this laboratory was designed from the ground up, literally, to house our very sensitive instruments. We're really proud of that. Come on, let me show you around. This is actually a separate room in the laboratory that is a micro distillation facility. And these are actually very small stills that mimic the stills out at the farms. The farm stills are often huge. They can be up to 18,000 liters in size. These obviously aren't that large. But what we do with these in this laboratory is bring in experimental plants from our greenhouse, and then we distill them and we collect the oils, and here you can see some oil that we collected earlier. And then we test those oils to understand what novel plants can bring us in terms of the oils. Now let me show you how we do some of the testing. I'd like to show you one of the real workhorse instruments that we use here in the analytical laboratory. It's called a gas chromatograph, or a GC. And this is actually one of the real workhorse scientists that we have in the laboratory. This is Dr. Richard Carlson, who is our Executive Director of Research here in the D. Gary Young Research Institute. Rich, what are you working on?
I'm looking at a juniper sample that we distilled in our distillation lab, and now we're separating all the components that were in that essential oil and trying to identify each of those separate components.
So this is real Utah juniper that's native to the state here?
Correct. Correct. Gas chromatography is such a powerful technique because we use it to separate very aromatic compounds. The molecules that we smell immediately when we open an essential oil, those are what we call as volatile compounds. They're usually very small molecules, and essential oils can contain hundreds of these molecules.
And they're volatile because they evaporate. And
Correct.
if they didn't evaporate, you actually couldn't smell them, is that right?
Right, right. One of the key components of the gas chromatograph is the column. Now this is an open tube. It's wrapped around this frame so that it easily fits inside the oven. This is about 60 meters long, wrapped tightly, and on the inside of this open tube is a very special coating. And that special coating interacts with the sample as it flows through the tube, and the molecules get separated into their individual components.
So this column or tube is not much thicker than the diameter of a hair.
Correct.
But it is an open tube that things flow through constantly.
Yes, and it's a very delicate process to put that polymer inside the tube, and a lot of science and research involved in making this consistent, and so we get the same results every time when we analyze a sample.
Good. Where does the tube go? You want to open the instrument and show
Yes.
everyone?
We install the tube in a very specific manner. This square box is what we call the oven. It's a heated zone. Very precise heating parameters are used. The column is installed in what we call the inlet. The sample is placed in this section, and then it travels through the column and it exits through here into what we call the detector. This particular instrument has a flame ionization detector which measures the amount of each molecule that's present as it's separated in the column.
Okay, so why don't we take a look at the output of a typical GC run?
Okay. The compounds, these numbers along the top of these peaks, as we call them, each peak is a separate molecule, represent the time that it remained in the column. And as they travel through the column, they separate out, they come out at a certain time, and each time we see this molecule under these conditions, it's going to come out at this exact time.
So this x-axis is actually minutes. So for example, this peak came out at almost 39 minutes. We had to run the instrument that long before that particular compound made it through the column and hit the detector. Is that right?
Right. And typically we'll run these for an hour, maybe 70 minutes. It depends on the sample, and we know what we're dealing with in most cases, so we know how long to run it. In the cases that we don't know what we're dealing with, we'll make sure we run it long enough so we get everything that's in the sample coming out of the column.
So one of the great things about an instrument like this is it will separate the oil into its individual components and identify those components. It will also measure the quantity of each component so that we can assess the purity and the potency of the oil. And it will also identify any peaks in there or compounds in there that shouldn't be there. So it'll actually be a very good measure of the purity and the naturalness of an essential oil. So this is another very sensitive instrument that we use to characterize the molecules in essential oils. And this is called a Fourier Transform Infrared Spectrophotometer, or FTIR for short. So this instrument actually shines a beam of infrared light through an oil sample, and the way it works is you put a very small droplet of oil on the instrument, and there's a little hole in this plate where the infrared beam can travel. You swing this over, this is actually the infrared projector. So it shines the infrared light through the oil, and every molecule in that oil absorbs the infrared light a little bit differently. So if we scan all of the wavelengths of infrared light, we can also monitor all of the chemical bonds in the molecules in this sample. And what it gives you then is a very unique fingerprint of the chemical bonds in the oil. And this is what we're looking at here. There's what we call the fingerprint region, where different carbon and hydrogen bonds interact with the infrared light. This is a large CH3 bond. This looks like an NH bond, and over here we have an OH bond, which would be found either in water or a little bit of alcohol in the sample. So this provides a very accurate fingerprint of the molecule. And what that allows us to do is to make sure that we have the exact molecules in the oil that we like. It also allows us to measure the purity of those compounds. It's a great instrument. So now I'd like to show you two instruments that I'm really proud of. And the reason I'm so proud of these instruments is, one is they are extremely sophisticated instruments that take a lot of training to run. And because they're so sophisticated, no one else in the essential oil industry even has these instruments. So let me show you what they are. These are isotope ratio mass spectrometers, and we actually have two matching instruments. And you can see Dr. Carlson here is working on one of them. Rich, do you want to come over and talk a little bit about what these are and how they work, please?
Yeah, sure. You mentioned they're isotope ratio mass spectrometers. That's this big part down here is the mass spectrometer section. On top of it, we see something familiar, a gas chromatograph. Again, the gas chromatograph separates out the individual molecules that are in the sample, in the essential oil. And by separating them, we're able to look at each individual molecule independently of all the others. We just talked about the FTIR. That looks at all the molecules together when we do an analysis using FTIR. But using the gas chromatograph, we separate out the individual molecules, and then each molecule is compared to a standard reference molecule to make sure that it comes from a natural origin. It does this by examining the carbon in the sample versus carbon in our reference material. And because we've been doing this for many, many years, we know what that ratio should be for each sample.
What we're actually doing here is comparing different isotopes of carbon. So there's carbon-12 and carbon-13 and carbon-14. And these instruments are actually able to identify and quantify the ratio of the various isotopes of carbon, which occur naturally in our atmosphere and then get into the plants as they perform photosynthesis and take in CO2.
By looking at each of these molecules as they are separated through the gas chromatograph and comparing that isotopic abundance, we call it, we're able to understand, did this get created in a laboratory somewhere, or did it really come from nature?
And as I said, there's an isotopic ratio that's kind of fixed in the atmosphere. So if the plant takes in the isotopes from the atmosphere, the plant will have the same ratio, and then the oil from the plant will have the same ratio. If it doesn't have that matching ratio, then we know it's synthetic.
And we can even drill down and understand which part of the country, which part of the world, where did this come from based on rainfall, based on atmospheric conditions and so forth. So it is a very powerful technique.
And extremely sensitive. So we can tell, for example, if a sample came from, let's say, Madagascar versus Mexico, based on the ratio of the isotopes that are in it. Really a great instrument, and we're really proud of it. In fact, we will be having a paper published on this very soon. We just submitted it to a journal, right?
Correct.
Yeah.
Correct.
So in this section of the lab, we have a suite of instruments that we call liquid chromatographs. And these are used for compounds that are not volatile, compounds that don't evaporate so that we can't use them in a gas chromatograph. And actually down here is Dr. Chris Bowerbank. And Chris is an expert analytical chemist, expert chromatographer, and he's actually working on, I believe, some new methods to detect some synthetic compounds that could possibly occur in vanilla.
Right.
And Chris, if you don't mind, maybe you could talk a little bit about how the instrument works and what you're doing.
You bet. As Dr. Buch mentioned, we're working on advanced detection technologies for analyzing and detecting both natural and synthetic components of our vanilla. This is a liquid chromatograph mass spectrometer, and much like the gas chromatograph that Dr. Carlson and Dr. Buch showed you earlier, in this method we use a liquid to push the sample through a column that looks like this. This is packed with small little beads that are coated with a polymeric material, and as the sample travels down the column, they separate into their individual components. Now this instrument here is what's called ultra high pressure liquid chromatography. As components are separated on the liquid chromatograph, they're then pushed over to the mass spectrometer detector. Now this is a single quadrupole type of mass spectrometer, and what this detector does is it actually determines the mass of the components as they exit the column. And based upon that mass, we can detect and identify what those individual components are. And as we compare those to a standard, we then can confirm whether or not those components that are coming off the column from the sample are authentic or synthetic.
And this is an instrument that we use typically to measure compounds that are not volatile, that don't evaporate, like in the gas chromatographs.
Right.
And these are particularly useful for things like vanilla that don't have a lot of volatile components, and also for vitamins. So we develop a lot of methods here to determine vitamin concentrations that we then transfer to our other laboratory in quality control that uses them to analyze samples every day.
Yep.
Thanks, Chris.
You bet.
So I wanted to show you one of the really cool attributes of these gas chromatographs. We can load up samples into little vials that have rubber tops on them. They're called septa, and place them in a carousel loader like this. And this is actually a robot. And what it does is move an arm with a needle on it that comes down and punctures the little rubber septum, and then takes a sample and injects it automatically into the instrument. So an analyst can actually load this up with all kinds of samples. I think this holds 24 samples. and walk away from it. And the instrument will run all day, and at the end of the day we can come back and look at the results. Fantastic little robot. I'll show you how it works. So now it's actually drawing the sample up into the needle, into the tubing, which will then go over to the inlet port on the GC and inject the sample. After the first sample is injected, it's timed to allow all of the components to separate through the gas chromatographic column, and after that first experiment is completed, it'll move automatically to the next sample and start again. So this is our pesticide testing laboratory. And I apologize, it's very noisy in here, and that's because the particular instruments that we use require strong vacuums. So there are vacuum pumps in here that are running all the time. But I wanted to point out the fact that this is a completely separate room from the other laboratories, and that's because we never want to take a risk of having pesticides contaminate our other samples in the other lab. So we're in a dedicated room with a different air handling system and different instruments that are used only for pesticide measurements. Again, this is a very sophisticated gas chromatograph with a mass spectrometer on it that we use to develop methods to detect very specific pesticides at very, very low levels. These days, pesticides are everywhere. They're even in the air that we breathe all the time. So we have to be very careful how we set up analytical methods to detect pesticides or potential pesticides in any oil or raw material that comes into Young Living. So here we are in the nutrition lab. Now we've transitioned from analytical research type laboratories into another type of laboratory, which is our product development laboratory. This is where we actually develop new products and make all of those great products that you love to use so much. So this is Varun Kaneru. He's the head of our product development team. And I think Varun has the most interesting job in all of Young Living because he and his team are the folks who actually develop new products, make the new products that you see every day, every year coming out of our labs. Varun, why don't you show us a little bit about what you do in here?
Sure. So after we do a lot of research on ingredients, we start procuring our ingredients to do more benchtop work. So here we have our whole library of ingredients. Once we procure the ingredients and know the research behind it, we make prototypes before we go into large scale-ups. So we have a kettle here where we can make liquids. We have a V blender where we can mix powders together in a good homogeneous mixtures before we going into the tableting and capsuling.
So Varun, over in this part of the lab, I know we have some equipment that allows us to mimic what happens on a larger scale in manufacturing. And specifically, we can make things like capsules and tablets on some of this laboratory equipment. Do you mind explaining how these
Sure.
work to some of the folks?
Sure. Once we go from the powder mixes, we take the mix and do more lab scale-ups for the press tablets, and we test them before we go into full-scale production to ensure the actives are staying intact and we have accurate formulations before going into the production.
So, I shouldn't talk with my mouth full, but every time I come into the nutrition lab, I like to sample some of the products that they're making here. And one of the things that I wanted to point out about this lab is that it's also a fully functional kitchen. So Varun's over here in the kitchen area, and I'll let him talk to you a little bit about that.
Hi. So here we have highly sophisticated 6-burner kitchen where we can create some of these food products in our labs. We have some of the most recent, your favorites, like protein bites or Wolfberry crisp bars are created in this lab. Also, vitality drops and few other products. Also, I want to point out some of our scientists. We have 3 certified food scientists, and collectively, we have over 40 years of creating natural products in this industry, and all the new and improved products you see are created by these scientists. And having this sophisticated lab really helps the scientists to thrive and be creative when they're creating new products.
This is our engineering laboratory, and this is where we work on physical devices that we sell at Young Living. So for example, this is where the diffusers are invented and tested. And you can see some of the new diffuser engines being tested here. And we have special venting systems so that we can run 100 diffusers at a time with all different oils. And it goes up into the vents and it's scrubbed before it goes out into the atmosphere. It's a great testing facility. So here we are in the personal care formulation laboratory. And this is where great scientists like Katie here develop all those wonderful personal care products that you've come to know and love. Things like all of our makeups, things like toothpaste, hair care products. And I'm going to turn it over again to Varun Koneru, who will take you through some of the specific things that we do here in this lab.
Along with the formulations, we have a lot of sophisticated instruments in our lab to test the efficacy of the products. So when we develop our skincare products, we have an instrument here called Vizia, where we have a phase scans on the optical rotation, where we can test, once the product is applied, have phase scans with different directions and have facial measurements, mostly of the physical parameters of the skin, and look at how the products, when applied, are working on them. And also we have our stability chamber where we test once we create these formulas, we test for shelf life of it in there. And I'll show you real quick how we work on those. Once we have a formula in the lab, we test it under stressed conditions to make sure it is having a full shelf life, which is a year to 2 years. And the instrument here we have is a 40 degrees C with a 75 humidity. And under those stress conditions, we look at our formulas to see how they behave under these stress conditions to know the full impact of the formula and the durability of it.
So I hope you've enjoyed your behind-the-scenes tour of the D. Gary Young Research Institute. And if you're ever in Lehigh, Utah, please come in and visit us at the Global Headquarters building and take a look at our laboratories. We have a lot of it behind glass, and you can come in and do a self-guided tour anytime you'd like. As always with Young Living, everything is open to the public. We have nothing to hide, and we love showing it to you. Thanks, everyone.